Okay, we're back for our asynchronous part 2 of the asynchronous lecture for Wednesday, September 23rd. And we're continuing talking about the principle of inclusion and exclusion. So we saw that the case where it's for one set inside of a universe, we could think of it as difference principle. And then it says something very simple. For two sets, it tells us about the cardinality of the union minus a union, the universe minus a union, everything outside of A1 and outside of A2. So outside of the union, A1, union, A2. So things that are in neither A1 nor in A2, another way of saying it. And then we get this slightly more complicated summation with a plus, a minus, and a plus. And then for general n, we were saying that there's a similar pattern when we want the complement of a union of these n sets, which we're abbreviating that union like this over here. That's just the same as this union. Then we first take with at k equals 0 a plus. We didn't talk about how do we interpret the k equals 0 term with the plus. That is the empty intersection. So it's the intersection of none of the AIs. And we think of the empty intersection as being the universe U itself. So that's the appropriate convention. Let me emphasize that since we didn't say it before. The k equals 0 term is U itself, the cardinality of U. When you're looking at the empty set of indices and intersecting an empty set of AIs, you get the universe. Okay, so let's do some examples. And the first two examples are going to be using the n equals 2 case of PIE. So I think we actually already did one of those that had to do with the languages in the school, but let me phrase some that are a little more interesting that show you how to do some general analysis for certain classes of problems. Okay, let's ask this one is, how many rearrangements are there of the letters in a certain word of, okay, the word is going to be, well, it's actually an Italian word, bambini. But I mostly care about how many repeated letters there are of each kind. How many rearrangements of the letters in the word bambini? And I mean possibly nonsensical rearrangements. They don't have to make any sense at all. But we know the answer to that problem. We already talked about it as a multinomial coefficient. It has to do with how many B's, how many A's, how many I's, how many N's, and so on. But I want to ask, how many of them avoid consecutive double letters within the word, by which I mean, well, since the only letters that end up being repeated here are the B's and the I's, I'm saying how many of them avoid having BB next to each other and also avoid having II next to each other. That is, avoiding BB and also II. Okay. I guess that's a question, so it should have a question mark. Well, so like I said, we do know sort of the universe here, all rearrangements of bambini. If we didn't say that we had to avoid certain sets, certain bad events, then we know how to count the total number of rearrangements. And so in problems like this, when you start to think that like, oh, there's some overlap that I have to take into account, the difficult part is often figuring out, can I use inclusion-exclusion to say this is really the same as the elements in a certain universe that avoid being in a certain union of sets that have overlap. And here we can do that. Okay, so if we make U be all rearrangements of Bambini, any kind, not worrying about consecutive letters. And then if we think about it, are there some sets that we can define, some A1, A2, whatever, A3, we don't know how many sets, that we're trying to avoid the union of those sets. And if you think about it, the set A1, if we define it to be those with a consecutive, by those, I mean those rearrangements of Bambini, with a consecutive BB. And if we define A2 to be those with a consecutive II, then this question is asking us, what's the size of U minus the union A1 union A2? So we want, I claim, the cardinality of U, but not A1 union A2, because this set, right, is those with either or both. Right? And that's the set we're trying to avoid. So we're trying to find the cardinality of this complementary set. Okay? So once you've got it set up to this stage, then you've got half the battle. You really have realized that, like, okay, this is asking me something that I have some hope that maybe PIE can apply. The second part of the battle, you know, the other place where things can go awry and not work is the PIE says, oh, when I want to get this, what I need are the cardinalities of all the intersections. Can I get formulas for those, including this empty intersection where you're not intersecting anybody, the k equals 0 term? Well, we decided, yeah, we do know the cardinality of U, so we're good there. And then there's the question, can we count the rearrangements that have the BB together? But if you go back and look at your notes or remember from some earlier days, after we talked about counting the rearrangements of a bunch of letters using a multinomial coefficient, we also figured out how to count only those words that had certain pairs of letters stuck together. We think of them as like a super letter, and then we're just working with a different set of letters and looking at all rearrangements. So we can count the ones that have this super letter BB. That's going to be another multinomial coefficient. We'll figure it out. We can count the ones that have this super letter II. That's a multinomial coefficient that we can figure out. And then what we're going to need to know is this. Okay, so let's take this over to the next page and see if we can figure out the pieces in that puzzle. Do we have the ability to calculate all those intersections? So when we do, whoa, a little crazy. Oh, now I can't rotate it. Yes, I can. All right, let's put this up here. So we're trying to get cardinality of U. Let's try that again. This is cardinality of U minus cardinality of A1 minus cardinality of A2 plus cardinality of A1 intersect A2. And for U, right, what we decided is, okay, so Bambini has two B's, two I's. What else does it have? Everything else is single letters, right? A, M, and N. And so that is a total of 1, 2, 3, 4, 5, 6, 7 letters. And we've got 2, 2, 1, 1, and 1 on the multiplicities. So this should be a multinomial coefficient. 7, choose 2, 2, 1, 1, 1, because we solved that problem before. This was one of the problems that we solved using our overcounting. What did we call that? Shepard's principle, or counting in two ways, or overcounting principle. Okay, so that's the cardinality of U. We're good on that. Done. Then we're supposed to subtract the cardinality of A1. And so in A1, right, those are the ones where we've got this consecutive BB. So the BB we think of as BB. It's like a super letter, blah, blah, blah. And so we just say to ourselves, okay, there's this super letter BB that we now think of as a single letter. There's the I, the A, the M, and the N. So there's two of these, one of those, one of them, and one of those. Okay, so the point is the BB is just now thought of as a single letter. And so if we take all the rearrangements of the super letter and the I's and the A and the M and the N, that gives us the things that are in A1. And so that cardinality is, again, a binomial coefficient. We've got a total of how many letters here? 1 plus 2 plus 1 plus 1 plus 1 is 6. And so it's 6. Choose 1, comma 2, comma 1, comma 1, comma 1. And let's not worry about evaluating these numbers yet. Right? We know how to do multinomial coefficients. It's a factorial divided by a bunch of factorials. Those are not hard. Okay, that's cardinality of A2. Sorry, A1 was this. Then for A2, what are our letters? So there's a super letter II. And so now I'll just say we've got the B, the II is a super letter. There's one of those. There's two of these. We've got the A, the M, and the N are each 1 and 1, 1. So it's 6, choose 2, 1, 1, 1, 1, 1, 1. Is that too many ones? No, that's the right number of ones. And then we realize, A1 intersect A2, right? Those are the things in which you've got the BB, the super letter, and you've got the II as a super letter. And so now you've just got a whole bunch of letters, right? Plus, so what are the letters? BB is a super letter. II is a super letter. And then A, and then M and N. We've got one of those each. So this is just 5, choose 1, 1, 1, 1, 1. Okay, so let me emphasize this thing. These, that's the cardinality of U. And this is the cardinality of A1. Oh my gosh, can we do this without getting the colors wrong? No, bad color. Yes, better color. And this is the cardinality of A2. And that's that. And cardinality of A1 intersect A2 is some other color, blue, and that is this. I couldn't get it all right. Okay. And now if we want, we can actually, evaluate this. It's not too hard. We've got the, I guess we could do this in red, is 7 factorial divided by 2 factorial, 2 factorial, and then there's a bunch of 1 factorials, but I won't even write them. Minus, what's the next one in green is, A1 is going to be 6 factorial divided by a 2 factorial. And then we're still going to have a minus. This pink thing is 6 factorial again divided by a 2 factorial. And then we're going to have a plus. This thing that's blue is just a 5 factorial, actually. Okay, and that's our answer. And I'm not going to evaluate it for you, but we could compute it. It wasn't so hard. Okay, so it was just n equals 2 PIE to the rescue. Let's try another example. Okay, we talked a little bit about how we know how to do block walking. And then I showed you how to use difference principle to do a block walk that went from somewhere to somewhere, but avoided a particular point where right at that corner was somebody that owed me, excuse me, I owed money. So I wanted to avoid them seeing me. But you know, what if I borrowed money from two people? And so there's these 2 points that I want to avoid. How many walks from, okay, standard situation, 0, 0 to 5, 10 in the plane. Again, taking the usual unit north and east steps. Those are the only kind of steps you can take. Avoid both of these bad corners that I really don't want to be seen at. 2, 6 and 4, 8. So picture would be, where am I going to? 5, 10? Yeah, 1, 2, 3, 4, 5. Okay, so 5 there. 10. Let me see if I can get these tick marks decent. Or let's say that's 5. That's 10. 1, 2, 3, 4, 5. 5. Okay. So there we start at 0, 0. And up here we're at the place I'm trying to get to. I am avoiding, what is it, 2, 6 is up here. That's a bad place. And let's see, where else? 4 and 8. Let's see, so in terms of tick marks, here's the 4. Here's the 8. Looks like I'm trying to avoid that place too. Oh, bad coloring. Don't want to go there. Okay, so imagine then I very carefully do my walking and I say like, I think I'll go east, east, and then maybe I'll go north and maybe north and then maybe east and then I'll go north for a bit. Getting dangerously close to that corner. I don't know, you know, I'm gonna, where am I now? That's at, yeah, 4. I'm already at 4. Okay, so I go up here. Maybe I'll do this. Anyway, that's one of these walks that manages to avoid them both. And let me just emphasize where these bad spots are. Right, that was the 2, 6, and that was the 4, 8 that I was trying to avoid. Okay, and now we have a little more experience here because we're saying like, aha, I'm avoiding both the 2, 6 and the 4, 8. There is some overlap between the things that, you know, are bad because they go through 2, 6 and the things that are bad because they go through 4, 8. You could go through both of them. That would be really bad. Okay, I'd be seen on both corners. So again, it looks like we're trying to avoid some sets and those sets have some overlap, and we eventually start thinking about this and might realize, aha, it sounds like it could be 2 set principle of inclusion exclusion if I can set up the answer right. So let's, with a little more experience, say, yeah, I think it is. This answer is cardinality of U minus a union of 2 sets that I'm trying to avoid. So it's going to be U minus cardinality of A1 minus cardinality of A2 plus the cardinality of A1 and intersect A2. And let me just save a little space by saying what these sets are right here. So the A1, excuse me, the universe is all the walks, where I don't care whether they go through any of the bad points. And A1 is the walks that go through 2, 6. They're bad because of that. And they might go through 4, 8, I don't care, but they at least go through 2, 6. And 2 is the walks that go through 4, 8. And remember, we feel good about those sets as things that we're going to be able to calculate because we have some experience from when we were just avoiding going through 2, 6. We did figure out how many of them went through 2, 6 as some product. So we're not too worried about our ability to calculate these cardinalities. But then this intersection is the walks through both. Does that say though or through? Let's make sure it says through. Through 2, 6, and 4, 8. And that's the question is, are we going to be similarly able to count those? And we can. So let's just think about how we did this, right? So let's do the answer. Again, let's maybe do some color coding. So this one is going to be in red, and we know how to do that. That thing is, what is it? It's 5 plus 10 choose 5. All right, we just take the m and the n, and we say it's m plus n choose m, or m plus n choose n. It doesn't matter. Those are both the same. And that was supposed to be in red, and I don't know what happened. Okay. So that's in red. Then we're supposed to subtract this cardinality of A1. Okay, we're going to do that in green. And so we take minus. And now this one we did know how to compute this. Remember, it was again some product of binomial coefficients. And basically the way we get the picture is we think about which binomial coefficient it is. Whoa, don't let that drift away. We take their picture and we say, oh yeah, here's the 5, 10. 5 and 0, no, 5, 10. And we want to make sure that we go through the 2, 6. And so we break it up into 2 pieces. There's the paths that go from the origin to the 2, 6. That's 2 plus 6, choose 2. And then there's the paths in the second half that go from, maybe I'll just draw a path and the path. Choosing that second path, we have to go over 5 minus 2 steps horizontally, that's 3 steps, and 10 minus 6 vertically is 4 steps, so it's 3 plus 4, choose 3. And no matter how we pick that first part of the path and the second part of the path, we can do them independently. It's product principle. We glue them together to get such a bad path that goes through 2, 6. And we don't care whether it went through 4, 8 or not. So good, we're done with that one. The A2, let's make it a different color. I suppose it's going to be, what did we make it before? I don't know, maybe it was pink before. Like this, and so we'll make that pink. And it's going to be a product of 2 binomial coefficients. And we draw ourselves a picture. And these things are supposed to go through 4, 8 on their way to 5, 10. And so they first do something in there, and the way they do that is in 4 plus 8 choose 4 ways, right, to pick the path that goes from 0, 0 to there. And then they follow that with a little path in the box from 4, 8 to 5, 10. So that goes over 1 step horizontally, 5 minus 4, and 2 steps vertically, so that's 1 plus 2, choose 1. Okay. And we missed some pink. And now we come to the most interesting part of it is what to do about this thing that's going to get some other color we have to decide, which is maybe orange. And now, how do we count that in orange? We make sure we have enough room. Do we have enough room? Plus, I think it's going to be 3 binomial coefficients multiplied together, because the picture is, I'm going to think of this walk, right? It starts at the origin. It's going to have to visit the 2, 6 via some walk. So that's the 2, 6. It's going to have to then visit the 4, 8 via some walk. And then lastly, it goes to the 510 via some walk. And choosing each one of those 3 walks in those little rectangles is counted by one of these binomial coefficients that we'll write down. And we're getting pretty good at writing down this one is what, 2 plus 6, choose 2. And let's see, the one that's in here between 4, 8 and 2, 6, it has to go 2 steps horizontally and 2 steps vertically. So it's 2 plus 2, choose 2. And then lastly, a little bit in that tiny box that goes from 4, 8 to 5, 10 is to go 1 step horizontally, 2 steps vertically. So it's 1 plus 2, choose 1. And that's it. It's this binomial coefficient minus this product of 2 of them, minus this product of 2 of them, plus this one. And that's these 4 terms. PIE with for n equals 2, again, it worked. Okay, so let's try one with a general n. I would feel bad if I had shown you the general PIE for any n sets and we didn't actually do an example. In fact, the example I'm going to do is the one I'm obligated to do. It's like every time someone talks about the principle of inclusion-exclusion for an arbitrary number of sets, just about every time this is the example that they're going to show you. So it's a fun one. That's why this is the one that we always pick. Okay, this is the famous problem, either called, I've seen it with 3 common names. The hat check problem. I'll explain the names in a moment. The hat check, or the derangement problem for people with French accents. And the third one you often see it as, or the Secret Santa problem. Okay, and so let me phrase it for you as the hat check problem. We imagine we're in, I don't know, 1940s, 1950s America and some fancy restaurant where people walk into the restaurant and there's N people, and those N people, they're labeled 1 through N. They're each wearing hats, okay? And they give their hats to the hat check person, but the hat check person is completely confused, forgets to, put numbers on the hats or names on the hats, doesn't label them, and at the end of the evening, just completely randomly hands back the hats to the N people. And the question is, what is the probability that nobody gets the right hat? Everybody gets someone else's hat. Okay, I'm gonna write that down. N people, each wearing hats, give their hats to the hat check person. Who later gives them back totally randomly. When I say totally randomly, what I really mean is where any assignment of people to hats is equally likely. This hat check person is drunk. All right. And then the question is, what is the chance that nobody gets their hat back? What is the probability that nobody gets their own hat back? What's the derangement? Why is it called that? Well, to derange is like to mix things up completely. And That's sort of like a French word, dérangement is like a complete disorder where everything is totally in the wrong place, a derangement. And then the Secret Santa problem is, this is something that back in the day when, nobody cared about whether one was celebrating Christmas or Hanukkah or Kwanzaa or any holiday, we would actually do this in school where everybody was going to have to give a gift to another student in the class. And you wanted to make sure that it really was to another student, not to yourself. You couldn't give yourself a gift secretly. So everyone was going to be the secret Santa who gave a gift to someone else. But how did we do the assignment of, which student would give a gift to someone else? We would each stick our names on a little piece of paper. The teacher would put it maybe into a hat. I don't know, hats used to be popular in those days. And the teacher would mix up the slips. Everybody would draw out a slip. And what you would hope was that nobody drew their own name. So that's the idea, is like the slips are the hats. Let's not get distracted by the fact that I said that we put them in a hat. Okay, think of the slips as the people's hats. Everybody randomly reaches in, grabs out a slip or a hat. And what you really want to happen now is that you get a derangement, so that everybody looks at the slip and says, oh, that's someone else, not myself, that I can give a Secret Santa gift to. So what's the probability that when you're drawing for the Secret Santa arrangement, you'll only have to draw once, that you won't have to fix the drawing because someone got their own slip back? Okay, so I hope the setup is clear. And what's interesting about this problem is we could figure it out for, n equals 1 and 2, what the probability is, or 3. But the question is, as n gets large, we're going to get a formula for this thing as a function of n, actually. We're going to compute this probability for all n. And we're going to use the general PIE for all n formula. But the question is, what would you guess happens as n goes to infinity, as the n gets large? Should we expect that this probability, now probabilities, they're always between 0 and 1. 0 is no chance and 1 is 100% chance, certainty. So the question is, do we expect as n gets large that the chance that nobody gets their hat back is getting vanishingly small? Like, is the limit going to be 0 as a function of n? Or should we think that, no, that's very likely that nobody gets their hat back, and as n goes to infinity, the probability that nobody gets their hat back is going to 1. It's like a certainty. I don't know. You might think that both of these possibilities might seem plausible to you. So let's figure it out. You think about it. Which one do you think? That nobody getting their hat back as n gets large, when it's 1 billion people, do you think that's vanishingly small probability? Do you think it's a certainty, or maybe something else? Maybe it's approaching some other number. Who knows? Okay. So let's get a formula for this probability. And as a function of n, figure out its limit as n goes to infinity. Or figure out how it behaves for n large. And the things we might wonder, does approaches 0, approaches 1. I think this thing wasn't really a question. I think that was supposed to be a period at the end of a sentence. So. Man, sometimes I just can't do it. Here we go. Okay. So what we're going to do, again, is try to phrase this as there's some sets that we're trying to avoid. We're trying to count the events. Oh yes, we should think about this too. It's a probability. There's all the ways we said that the hat check person could hand back the hats. That's all arrangements of the n hats. And we should think about that as being our universe. And do we know its size, its cardinality? Maybe I should say all arrangements, distributions of the n hats. If you think about that, you've got these n people, and then there's the n hats. To put those hats distributed to n people, this is just like taking the n distinct hats and linearly ordering them. It's like taking the numbers 1 through n and just putting them in order. Who goes to person number 1? Who goes to person number 2? Who goes to person number 3? That's just putting them in order. And that is n factorial. So I'd like you to think about that. Why is it that if we put the n people and then we take, the hats and arrange them like this is hat 5, hat 7, hat 1, hat 3 goes over here. Why the number of ways we can arrange the hats is n factorial. Okay, think about that. Good. So we can count our universe. That's good. But then the question is, can we set this problem up as trying to count the complement of a union of a bunch of sets that we're trying to avoid? And so that's the key in this problem, is trying to set it up that way and then hoping that we can count the cardinalities of the intersections of those sets. That's what we'll need in the general PIE formula. So I propose we let A1, A2 through AN, when we're counting these derangements, these hat checks distributions where nobody gets the hat back, let's let AI be the distributions where person I gets their hat back. Arrangements where person I does get their own hat. Okay, we're trying to avoid those. We're trying to avoid A1, union A2, union A3 up to AN. We really want none of those to happen. So we want to be in U, set minus the union, the complement of the union of the AIs. Okay, so that's the problem. Let me just take this over to the next page. If we set the thing up this way, we want the number of derangements, or the number of Secret Santa arrangements, is the size of U minus A1 union AN. We're trying to avoid all of those sets. Okay. And then PIE, right there, here's our buddy. PIE for n sets, finally, we're going to use the general one. Says, oh, we should be, counting this U minus the sum of the AIs. I'll write it in this form, plus the sum of the pair intersections, and so on. Let me for the moment write it like that, and then let's use the compact form that says, oh, sum of k goes from 0 to n. The sign is -1 to the k, and then we have to count this over all of these k-fold intersections. The cardinality of the intersection of those k of the sets. All right. If we can get at these numbers, we're good. We'll just plug it into this formula and just hope things don't look bad in the end. And this is a problem where they don't. So we work on it. And okay, so first of all, let's figure out what we know what U was. The size of U we decided was all rearrangements was n factorial. What about the cardinality of A1? So A1 is person number 1 got their own hat back, right? This is when I line up the people and we line up the hats. It's like, oh, H1 is there. And then the rest of them, I don't know what happened. Maybe somebody else got their hat back. I don't know. But the point is, at least hat 1 went to person 1. So I think I can count this. these arrangements that have this property that at least one got their own hat back, I just give them their hat, tell them to go off in a corner, and count the arrangements of the remaining people arbitrarily. I claim that's n minus 1 factorial. And in fact, I don't think it mattered that it was person number 1 that I insisted getting their hat back. Person number 5, if I insist that they get hat H5, again, make them go sit in the corner with their hat and everybody else just gets arranged arbitrarily. That'll count the number of such arrangements where 5 gets their hat back. So this is really for all I. Okay. You know what? I think I can count how many arrangements there are when we're in A1 intersect A2. Because I can picture that. I think, okay, here's 1, 2, 3, 4, and n lined up. And we've got these orange hats. I don't know how the hats got to be orange, but anyway, H1 and H2, they got their own hat back. Sorry, 1 and 2 got H1 and H2, they got their own hat back. And then the rest of them were arbitrary, you know. Who knows what happened? H5, H7, H8. So again, I would just send the 1 and 2 off into the corner and say, I'm going to arrange these n minus 2 others in n minus 2 factorial ways. And in fact, AI intersect AJ is the same. It's n minus 2 factorial. And so we're starting to realize that, let's get this. Number of derangements is this, which is this. I want to take too much stuff over to the other page. Go. I lost some of it. Okay, but the point is, U is n factorial, AI is n minus 1 factorial, AI intersect AJ is n minus 2 factorial, and you keep doing this and you realize, oh, when there's k of them, a k-fold intersection, you take those k people, you put them off to the side, and the remaining n minus k factorial, n minus k people, you just arbitrarily arrange their hats in n minus k factorial ways. It works. And so our answer, the thing we're working on up top there, is this. K equals 0 to n minus 1 to the k. And these things are, now we have to do something. We have to count how many of these subsets of k indices, I1 up to ik, that's a k element subsets of n, how many of these terms there are in the sum. Maybe I'll write this in 2 steps. It's for each of those, pick a k element subset, we're going to get an n minus k factorial. Well, we're always getting the same number, so I could pull it out here. And this is just a sum. K goes from 0 to n, minus 1 to the k, n minus k factorial. And then I just have the number of these terms in the sum is n choose k, because that's how many ways we could pick a subset of the indices I1 through ik. Okay, that's good, because I like the way this is starting to look. N minus k factorial, remember n choose k is, it's got an n minus k factorial down there. It's this. So this thing wants to cancel this thing, and this whole expression is turning into this. Ooh, not bad. Getting better. We've just counted how many derangements there are. Even better. Can we steal this? Oh, maybe, if we're lucky. Will it work? Yes, it'll work. So, number of derangements is that. Probability that we get a derangement is, it's that number divided by the size of the universe, all the arrangements, which is n factorial. Look at that. It beautifully takes away that n factorial that we had right there in all the terms. Remember, cardinality of u was n factorial. Oh, this is looking nice. So let's write it out. The k equals 0 term is a 1 over 0 factorial. Does anybody know what 1 over 0 factorial is? That's 1. 0 factorial is 1. Ooh, next term is minus. We're going to get a minus k equals 1 term. 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial and so on. And it ends with a minus 1 to the n over n factorial. So this is like 1 minus 1 over 1 factorial plus 1 over 2 factorial. Okay, so this gives us this probability for any n. And if you start tabulating these, you know, we can just like write these down for n equals 1, n equals 2, n equals 3. You'll start to see that they have a limit. That limit is not 0. That limit is not 1. When you take the limit as n goes to infinity, it's going to be 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus and so on. You realize, wait a minute, this is like an alternating series. When I took calculus, they told me this thing would converge because the signs are alternating and the terms are getting smaller and smaller. And in fact, I recognize it. This is the term like e to the x at x equals -1. Right? What I'm seeing in the numerator there is a minus 1 to the plus and minus. That's like a x to the n when x is -1. And so this thing is, that's e to the -1. This is 1 over e. It's approximately a third. It's like 1 over 2.7, 1 over 2.78. So this probability of a derangement, it doesn't go to 0, doesn't go to 1. It goes to about a third, which is a little bit surprising. Okay, I'll let you ponder that. Sorry, the recording went over a little while, but at least we got to a fun answer. I will see you on Monday for a synchronous class. Have a great weekend.